All right, let's jump right in. If you're an RF tech, you know better than anyone how crowded our wireless world is becoming. I mean, it's crazy out there, right? So mastering Wi-Fi configuration, that's not just some nice-to-have skill anymore. Nope, it's your secret weapon. It's what really separates the good techs from the great ones, especially when you're staring down a really complex, messy wireless environment.
And just so you know, what we're covering today is actually part 2 of a bigger 10-part series. It's all based on this incredibly detailed report from the folks at RFI Detectives, who are part of Virtualization Options LLC. So today, we're really getting into the nitty-gritty, the core configuration settings that every single technician has got to have on lockdown.
So let's not beat around the bush. Why does this matter so much? Well, the stakes are incredibly high. I mean, just look at this quote. A single tiny misconfiguration, like your channel width, can slash your throughput by 50%. But it gets worse. It can also create so much co-channel interference that it messes with a dozen or more of your neighboring networks. Think about that. That's the kind of impact we're talking about with these settings.
So here's our game plan for today. We'll kick things off with the big picture, the modern Wi-Fi challenge. Then we'll dive into identity and access control. After that, the really fun stuff, tuning the actual RF environment. Then, we'll get into some advanced performance optimizations and wrap it all up with troubleshooting tips and best practices. All right, Section 1, the modern Wi-Fi challenge, and why every single setting matters. You know this. Think about the last time you were in an apartment building and you pulled up the list of available networks. It's just endless, right? Dozens and dozens of SSIDs. We're fighting for airspace in these incredibly congested RF environments. And honestly, smart, deliberate configuration is our best tool for cutting through all that noise.
You know, getting configuration right isn't just about cranking up the speed. It's more like a balancing act. You've got these 4 pillars. You've got network performance, that's your speed, latency, all that good stuff. Then there's security, obviously. You've got RF efficiency, which is all about playing nice with your neighbors and not wasting spectrum. And finally, client compatibility, making sure everything from that brand new laptop to that 10-year-old printer can actually connect. It's a giant puzzle, and every setting is a crucial piece.
Okay, that leads us right into Section 2, Identity and Access Control. This is really ground zero. We're defining what the network is and, maybe more importantly, who gets to get on it. And it all starts with the SSID, you know, the network name. A good SSID isn't just a funny name, it's a tool. Think about how much easier troubleshooting is when you see a name like Building A Floor 2 5 GHz instead of FBI Surveillance Van, right? And even more critical is using different SSIDs to segment your network, keeping corporate, guest, and all those IoT devices separate. That's a security must-do.
Okay, now for the big one, security. This table just lays it all out, right? The evolution of our security protocols. And honestly, the takeaway here is super simple. WEP, it's broken, completely. Never, ever, ever use it. WPA with TKIP, it's weak, and you should only even think about it for some ancient device you absolutely have to support. And even then, stick it on its own isolated network. For today, WPA2 is your solid baseline, but WPA3, that's the gold standard we should all be aiming for.
So what's the big deal with WPA3? Why is it so much better? Well, it comes down to a couple of game-changing things. First, it kills the old handshake method and brings in something called SAE. All you need to know is that this makes it way more resistant to those offline dictionary attacks, where a hacker tries to guess your password over and over. And second, and this is huge, it makes Protected Management Frames, or PMF, mandatory. This is what stops those nasty deauthentication attacks, where a bad guy can just kick your devices off the network. It's a massive security upgrade. All right, let's get to the part every RF tech loves, getting our hands dirty with the RF environment itself. This is where we get to tweak the actual physics of the network to squeeze out every bit of performance.
First thing we've got to talk about is channel width. And the key word here is trade-off. It is always a trade-off. Sure, wider channels like 80 or 160 megahertz give you this big, wide pipe for more speed. But they also eat up a ton of spectrum, which leaves you with fewer channels to choose from and a much higher chance of stomping all over your neighbor's signals. And for the 2.4 gigahertz band, just don't even think about it. The best practice is simple. Stick to 20 megahertz channels. Full stop.
This brings me to a classic debate, a question I see popping up all the time. When you're setting up your access point for transmit power, should you just crank it to the max? Is maximum power always the best choice?
Well, let me give you the authoritative answer. Absolutely not. The report says it perfectly. This is one of the biggest misconceptions in the world of Wi-Fi. Blasting your signal at full power sounds like it should work, right? But in reality, it almost always creates more problems than it solves.
And here's the reason why. It creates a problem called an asymmetric link. Imagine your powerful access point is shouting its signal across the room. Your little smartphone can hear it just fine. But then when your phone tries to whisper back, its tiny little radio is too weak, and the access point can't hear it. So what happens? Your phone shows 5 bars of signal, but your connection drops constantly, or doesn't work at all. This is why in crowded areas, turning the power down is often the secret to a better network.
Okay, let's level up. We're going to move on to some of the more advanced tech that's baked into modern Wi-Fi. The stuff that helps us get every last drop of performance out of the airwaves. We're talking MIMO, beamforming, and QoS.
First up, MIMO. That stands for multiple input, multiple output. The easiest way I can explain it is this. Think of it like turning a single-lane country road into a multi-lane superhighway for your data. By using multiple antennas, MIMO lets the access point send and receive several streams of data at the exact same time. The catch, though, is that both the access point and the device, your laptop, your phone, they both have to support the same number of streams to get that full superhighway benefit.
Now, beamforming kind of takes MIMO and makes it smarter. Instead of the access point just blasting its signal out in all directions like a big, dumb floodlight, beamforming acts more like a super-intelligent spotlight. It uses its antennas to focus the RF energy directly towards the device it's talking to. This does 2 amazing things. It boosts the signal for that specific client by a very real 3 to 6 dB, and it reduces interference for everybody else. It's a win-win.
And finally, let's talk about QoS, or quality of service. So by default, a network is pretty dumb. It's first in, first out. That means your super important Zoom call has to wait in the exact same line as your coworker's massive file download. QoS completely changes that. It's basically a traffic cop for your data, waving the important time-sensitive stuff through the intersection and making the less critical traffic wait its turn.
And this slide just lays it out perfectly. Let's go back to that highway analogy. With QoS, your voice calls and video conferences, they're in the express lane. They absolutely cannot be late. Video streaming like Netflix, that's right behind them in the fast lane. Regular web browsing is just cruising along in the middle lanes. It can handle a little delay. And that huge semi-truck carrying big file downloads and backups, it's chugging along in the slow lane. It'll get there when it gets there, and it's not holding up any of the important traffic. Okay, so we've covered a ton of theory. Let's bring it all home now in our final section. A super practical checklist for troubleshooting, and a quick summary of the best practices we've been talking about.
Look, when things go wrong, and they will, the worst thing you can do is just start randomly changing settings. You need a process, and here it is. Step 1, define and document the problem. What are the exact symptoms? Step 2, look at the physical layer, measure your RSSI, check your SNR, scan for interference. Step 3, review the configuration, go through all the settings we just talked about. And finally, step 4, test systematically. Please, please, please change only one thing at a time and write down what happens. That's how you solve problems.
And here it is, the moment you've been waiting for. This is the cheat sheet. Go ahead, take a screenshot of this, burn it into your brain. For 2.4 gigahertz, it's simple, channels 1, 6, or 11, and a 20 megahertz width. And notice the power setting, well below max. For 5 gigahertz, you've got more flexibility with channel width, but look at the power, it's even lower, often just 25 to 50%. We want smaller, cleaner, more efficient cells. And of course, for security on both bands, WPA2 is the absolute minimum, but you should always be pushing for WPA3.
And that kind of brings us to our final thought for today. We've seen just how powerful intelligent configuration can be. But as our wireless world gets denser and more complex every single day, it makes you wonder, right? At what point do we hit a wall? Where does tweaking the software settings end, and the need to fundamentally change the physical infrastructure, the hardware, the AP placement, begin? That's really the core challenge for every modern RF technician out there.